Okay, we are going to discuss about homework 6 solution. The first question is about slider and crank mechanism that I'm going to open that. Okay, 1 second. It would be okay. That's the assembly that I have opened. I think there is nothing in the motion analysis, so we can start it. So let's going back to the question. It says use the same slider crank mechanism to find the equilibrium configuration of the mechanism to the gravity. So meaning that the only applicable actuation is the gravity, and by the weight of the component is going to stay at some positions. We need to introduce some dampening effect to the whole assembly, and the reason is if we don't, then it's going to oscillate forever and there is no damping. So and the damping that this question has been suggested is essentially a torsional damper between the crank and the bearing part, which would be here, the crank and this bearing. So we are going to define a torsional spring between them. Then it asks for the spring constant to 0, so there is only dampening effect. We are going to submit the horizontal linear position and the velocity of the piston, back and forth, and the velocity. And then it asks what is the angle between the link, between these two links in the equilibrium position. Okay. And the second part of the question one, it wanted to change the length of this length from 3 to 5 inches and run the analysis, meaning that it's similar to the class 60 RPM we are going to apply to the crank and no damping or gravity would be available. Then we are going to submit linear velocity of the acceleration of the piston for 1 second, horizontal reaction force between the pin and the piston, and so on and so forth. So let's start with the first part of the question, and we move on that. So first we are going to change the mate, make sure that the assembly can move. Currently, yeah, assembly has 1 degree of freedom. I think it's ready because the coincidence has been turned off, meaning that this can easily move. So all we have to do first, we are going to apply gravity on y direction. Okay, that would be here. And then essentially what they wanted, I think we can give them enough time, but let us start by give it like 1.5 seconds, and we'll see if that gonna stay in the equilibrium position. The time is not given in the first part, so we are going to give some time as long as the assembly does not move. That's equilibrium position. We change the animation to the motion analysis, and then the gravity has been defined. We have to define the torsional spring, so we are going to go to spring, and now we select torsional spring. For the part, it says between the bearing and so essentially this between two faces of that. So okay, so for the spring parameter for torsional, we might not practice it in class, but it's very easy. They wanted to, we have to give them an axis of the rotation for the spring. So while there are multiple options to doing that, we can either find the faces here that these two rotate against each other. What we can do is we select this face and this face, essentially, because this is belong to the bearing and this is part of the and you see that it's going to give us that direction, that how this direction would react. The orientation does not matter here because the K would be 0 and the dampening effect would be linear, and the value is given as 0.005. Then hit OK, and then give it some initial velocity. Let's go to take a look at the frame per second. I'm going to stay with let's say 200 frame per second. I think it's not given the actual frame per second, so we can select any number essentially. So when we remove it, it's gonna move. Okay, but still the assembly was moving. So to having a fair, I'm going to change it to, let's say, 3 seconds. I think that should be enough. So again, start, you will see assembly is going to move because of the gravity. The dampening is going to kill the velocity, and at some point this is gonna stay, and the assembly is not moving here. So we are going to submit the position, linear position and velocity of the piston. Going here, and it would be linear displacement. It would be along x-axis, so that's our linear displacement along x-axis, which is here, and we're going to select this component, which is gonna be here. It seems like this was a little moving here, so just to be safe, I'm gonna increase even to 4 seconds. Do the analysis one more time. It could be a little trial and error that if you have not selected the right simulation time, then I'm going to go to the result and I'm going to show the plot here, and now it's, you see that it's pretty much constant. So that would be the linear position. I will call it piston horizontal linear position. Okay, it's gonna be changed. I'm going to capture the screen result, which is here, and that would be save. Okay, that would be homework 6 Q1-1 or Q1A. All right, and then for second graph, it wanted a linear velocity. So I'm going to go here, linear velocity, and that would be across x-axis, and piston is the selected component, and okay, that would be the linear position, and call it that as well for this, and that is gonna give us the this one. Okay. All right, so, and then it was, what's the angle between the links in the equilibrium? And essentially, essentially what we are going to do here is we are going to bring it to a point that we would like to know what's the angle between them. So in the beginning of that, so in order to find the angle, one of the best things is we find the plane between them and find the angle. So I'm going to go here, and it would be linear displacement, and then essentially I wanted angular displacement. And what is the component that I'm asking is, first of all, the crank. See which plane represent the angle of the crank, which is right plane to do that. But select result component, right plane. Okay, sounds like we cannot select a component of that. We can select the faces. Why not? can select this face and this face, and pretty much that is going to give us the angle, and that's the magnitude of that, and that would be here. And the equilibrium position, the angle would be 179 something. So I'm gonna save this one as well. Now, the second part of the question, we have to, actuate by the motor. So I'm going to suppress the torsional spring, suppress the gravity, and add the motor here. And it's a rotary motor. I'm going to select this one. And it was giving me 60 RPM. However, it asks us to change the length. So if you double click on it, you will see that the part here is 3. You can go ahead and directly select this one to 5. And then if you hit here, then the assembly would be different. Of course, there is a lot of interference between the piston and here, but that's a way to go. So it says that, all of this pinches position. Sure, go ahead, no problem. So we have applied the rotary motor, right? Still is here, 60 RPM, everything constant. And now we can for sure just simulate the whole thing by 1 second. Nothing more than that is required. It would be 1 full turn. So everything is off. We calculate that, you will see that it's gonna have this motion. Now what is wanted is a few graphs. First, we wanted the linear velocity of the piston, which we had that linear velocity, I believe. Yeah, it would be piston linear velocity. And if I show the plot, that is the linear velocity of the piston, right? I'm gonna save it to and that would be my homework 6Q, but 1A, 1B would be Q1C. Okay, and it would be velocity, but we need an acceleration. So it would be, in order to get that, I can go ahead and select a different displacement. I wanted a linear acceleration across X component, and it's very boilerplate. That would be acceleration. I call it piston acceleration, and let's save that. It would be Q1D. And then you wanted a horizontal reaction force between pin and piston, meaning that what's the reaction force here. And then we can go to the mate and see essentially the mate that has been defined is concentric 3. So you know that we need that mate in order to create that. So I'm going to result, forces, reaction forces, and then we want it across X component. We want the horizontal component on that, and here you're going to give it the concentric 3. Between these two, it asks if it is going to be redundant. Yes, and that is the reaction forces, right? So that would be, I would call it pin and piston reaction force, and I'm gonna save that, which is gonna be E. And then what is wanted as the last section, submit the magnitude of reaction force between the crank and rod. So the magnitude of reaction force here. So again, we need to identify what is the mate that represent that, and we will see this is concentric 2. Very same approach. We're going to go back to forces, and then we are going to reaction force, and we wanted the magnitude of that, and the mate representing of that relation between the rod and the crank would be concentric 2. Hit OK, and that is the curve for that. And then this would be crank and rod reaction force. And saving this is going to conclude the question 1 of this problem. Going to be QEQF. Okay. We'll see you for the next question.